Hey gang, welcome back. We've got a little mechanics of material column buckling example today. We're going to be continuing our talk about column buckling, about Euler's buckling equation. Remember some things we talked about last time? These were our end, fixity, I think it's I. There's an I right there. Fixity, conditions. Okay, that's how our beam is going to buckle is connected on the ends, right? The end fixity conditions. Pins 1, which is also called, do you remember? Called ideal. Fixed, pin fixed, and fixed free, okay? So let's see if we can use these to solve this, okay? Now this looks like, right? That's a W. This looks like it looks like a statics problem, doesn't it? Okay, let's see what we've got here. Using a factor of safety for buckling of 1.5, find the max value for W, okay? This distributed load. How big is that? Can that distributed load be? Okay, they've given us yield stress, and they've given us the modulus elasticity for this material, okay? Now we have a cross section here, so it's 80 in this direction, which means it's 45 into the board, the thin direction. Now let's talk about that buckling for a second, okay? Now as that load increases, I got a yardstick here, okay? As that load increases, and it's kind of like this, right? Wide side, thin side, right? As that load increases, I don't know if you can see me bending that or not, right? But it wants to bend. Now I'm just doing pin with my fingers here, right? It's allowed to swivel, to rotate here at my fingers. And it wants to bend into the board, right? Now let's just call that for fun, okay? Let's just call this, bloop, the y-axis. Well, let's call it that way, arrow. And then the x-axis is coming out at us here, okay? So the x-axis is in this direction here, okay? Now if we have bending like this, right, where it's bending into the board, if you will, that's what we call bending around the y-axis. And that is the weak axis of bending for this beam because it wants to always fail on that axis, okay? It doesn't want to fail that way because it's thicker this way, right? So it doesn't want to fail that way. It will if somehow I can hold it and prevent it and make it buckle that way. I can't do it with my fingers on this. But the question I have to you, now, there's two things that change here. Number one is the moment of inertia definitely changes. So you have I, X, and you have I, Y, okay? Again, IY is going to be what we call the weak axis. IX is going to be the strong axis. That's probably one of the most confused things that students get this wrong, is they get these two things backwards. So what they should be using for the base, they use for the height, and what they should use for the height, they use as the base. So be really careful. I'm telling you, y'all, it helps you so much. If you can get one of those little metal 12-inch rulers, the little flexible ones, and in the test, you can kind of flex it. You can kind of go, okay, let's see, this is the base, that's the height, right? And you can kind of see that. It'll help you, okay? So let's talk about, so these two things here, I've got to get that sorted out. And I think that's pretty easy to do. The other thing that's most commonly messed up on these is what happens here and what happens there, okay? Now, in buckling, well, let me draw a little exaggerated buckle here, okay? Buckling in this direction, whoa, okay? There's two, there's that one, and the buckling into the board would just be a straight line, wouldn't it? Because you can't see it because it's going into the board. But the other one is the one that's bending that way, right? In that direction, in that bow direction there, when it bows, right? That pin gets to act like a pin. It allows the thing to pivot around a point, right? So in this direction here, which is bending around the x-axis, remember? Okay? It's going to be pin. But what about bending, it's into the board or out at you now, okay? What about bending in that direction? Well, that pin swivels this way, but it doesn't swivel this way, right? In that direction, actually, it's fixed, isn't it? It's fixed and fixed, okay? And now the end fixity conditions change. So for bowing or buckling around the x-axis, it's going to be pin-pin. And for buckling around the y-axis, into the board, if you will, is going to be fixed, okay? So those values right there are going to change for Euler's buckling equation. Now, do we remember Euler's buckling equation? Okay, it's this. P critical, the critical force that's going to make that thing fail, is equal to pi squared EI divided by KL quantity squared. Now, another big mistake I see students making, don't do this, don't be Johnny Weak Sauce here, right? Is it's KL quantity squared. Sometimes I see you just doing L squared here or putting the K on the outside, but the K goes inside the parentheses here, okay? That's a big one. Now, most of the time, beams are pin-pin, and we call that the ideal connection, right? And K is equal to 1, and so that just kind of goes away, and so it's L squared. So sometimes you'll see this equation written just like this, with just an L squared on the bottom. But that's assuming you have ideal connections, okay? And do we always? Well, no, okay? So what we're gonna have to do is we're gonna have to evaluate both conditions here. What does it take to make it buckle this way? And what does it take to make it buckle that way? We're going to get two P criticals, one for each one of those scenarios, and then we're going to have to choose which one is going to happen. Well, which one happens first? The biggest one or the smallest one? Well, the smallest one is going to happen first, right? Because once I get to that load, it's going to buckle in that direction. And so we're going to get two P critical values. We're going to select the smallest one to then go and calculate what is W, okay? Is that a lot? We got this, man. We got it. Let's do I first. Let's calculate I, okay? So here we go. Let's do this guy right here. We'll do around the X first, okay? So when it buckles around the X, okay? When it buckles around the X, right? The base is always parallel to the axis, okay? So we're doing skinny side into the board. So the base is going to be what? Well, it's going to be 45 is the base. Let's do 1/12, shall we? Do you remember this for rectangular shapes? 1/12 BH, which is 80 cubed, okay? Now it doesn't want to go this way, right? This way, whoop. It doesn't want to go that way. That's why I call it strong. The strong is always going to have, of these two numbers, the biggest one's going to be cubed. Duh. That's going to make I the biggest. That makes him strong, muy fuerte, no? Okay. And so the weak axis of bending is going to be 1/12. There's the 80. And look who's cubed now. Well, the 45, right? That's going to be a smaller I. That kind of makes sense, doesn't it? Strong axis, weak axis. Big number, smaller number, okay? Let's see what that number is, okay? On. 80 cubed times 45 equals, divided by 12 equals. And remember, these are in millimeters, so this is going to be millimeters to the fourth. Oh, it's a big number. Are you afraid of big numbers? I'm not afraid. Don't be scared. So 45 cubed times 80 equals, divided by 12 equals 607,500. Okay, so let's calculate P critical for bending around the x-axis. And remember, bending around the x is this way. So for bending around the x, remember this one was pin, and this guy down here was fixed. Now you might say, I already know it's going to bend around the weak axis because that's where it wants to bend. Maybe, but you know what? The end conditions change everything. I mean, it changes everything. Because it's going to change this number down here big time, and it's squared. So we better check it out. So let's do x first, bending around the x. So the P critical force to do that is going to be equal to pi squared times E, which is down here. Okay, now we're going to do this. We're going to do 200,000 newtons over millimeters squared, right? I turned it into megapascals from gigas, okay? Times I, which is this number, 1,920,000 millimeters to the fourth, okay, divided by K. What is K? For pin, it's 1, times the length, the unsupported length of the beam, which is 3 meters, which we're going to call 3,000 millimeters, okay? And then we're going to square that whole thing, okay? So let's see what that is equal to, okay? So pi squared equals times 200,000 equals times 192,123 equals divided by 3,000 squared, right? Equals, bam, 421.1. Now that's newtons, right? Everything's in newtons. I got 421,103, or I'm going to call it 421.1 kilonewtons, okay? Stone cold kilonewtons, yo. Okay, so here we go. Next one, P critical. Now we're going to do bending around the Y. Why? Because we have to. Okay, 200,000 times this value, 607,500, divided by, here we go. Now this one's fixed, so it's 0.5. So 0.5 times 3,000 times all of that squared. Boy. Let's see. So here we go. Pi squared equals times 200,000, 123 equals times 607,500 equals divided by 3,000 times 0.5, that's 1,500, right? 1,500 squared equals, bam, woo, 532.95. So 533. Kilonewtons. Okay, So what does that mean? This thing does not fail around the weak axis. It fails around the strong axis, right? Wow. Those end conditions changed everything, didn't they? Okay? So this is the number we're going to work with. Now that number is the absolute number that thing is going to fail at. You don't want to put 422 kilonewtons on there. It'll break. It'll fail. It'll buckle, right? Well, but what about this? It says use a factor of safety of buckling of 1.5, which means we don't want it to fail at 421. We want to fail at something less than that, don't we? Because we want to make it, we want to lie to them like the Ford F-150, right? It's a half-ton truck. You should be able to put 1,000 pounds in the bed. It's a half a ton, right? And that's what Ford says, half a ton. But I guarantee you they got a factor of safety. If you've ever been over to Home Depot on the weekend and people are putting like 3,000 pounds of concrete in the back of one of those, right? They make a factor of safety on that because they will break stuff, right? So how do I make that number a smaller number with 1.5? Multiply by 1.5 or divide it by 1.5? Divide, right? So 421.1 divided by 1.5 equals 280.73. So our real buckling number we want to use is 280.73, okay, kilonewtons. And that's got a factor of safety of 1.5 on it. It really fails at 421, but we're going to tell the public, yeah, 280 is all it's going to hold, y'all. But we got a 1.5 factor of safety built into that, right? So what we want to do now is, that is the number that when pushing down on here will make this thing buckle. So how big does W need to be for that? Well, what you have is this. We've got this distributed load. We've got a pin connection over here. This is statics, isn't it, y'all? Okay. And I've got this distributed load up here on the top. And how big is that distributed load? It's 5W, isn't it? Where'd that come from? 5 times W, pounds per feet, or whatever it is. I mean, not pounds per feet. It'd be kilonewtons per meter, wouldn't it? Okay. And then over here, it's going to take 280.73 to make me buckle. So how big is W? Right? Ooh, that looks like this, doesn't it? Take the moment at A, and what do we get? Remember, that's a rectangular distributed load, so we're going to put that right in the middle. Right? The 5W rotates me positive. So 5W times how far away? 2.5. Right? Minus 280.73 times how far away? 5. Right? The 5's divide away. Right? And what do I get? So W is equal to 280.73 kilonewtons divided by 2.5, which is equal to, divided by 2.5 equals 112.3. So that's what W would need to be, is 112.3 kilonewtons per meter. Remember, it's a distributed load. That's the maximum that it could be so that that thing doesn't buckle. Now, there's one more thing that you probably want to go check, and that is this, right? They gave me, why did they give me sigma yield right here, gang? Why? Well, remember, a beam can fail two ways. It can fail from buckling when you're in compression, or it can fail from just straight deforming, right? It just crushes it, right? So we could check that pretty quickly, right? We got 250 megapascals, 250 newtons over millimeter squared is equal to the crushing force that would take it to fail that way, divided by the area, which is, 80 by 45. And to be honest with you, I don't know that I've ever worked one of these problems where that actually failed because of this before buckling. But we check it anyway, right? So the force has got to be how big? So it's going to be, this is going to be 250 times 80 times 45 is 900,000. That's newtons, right? So the force that it's going to take to crush it is 900,000 newtons, or 900 kilonewtons. But it buckles at 421, right? So is it ever going to buckle? Is it ever going to have a compressive failure? No. Okay. So check mark, boom, boom. We are good there. Okay. All right, gang. We're getting awfully close to the end of the semester. I hope this helps, and I'll see you on the next video.